Okay, there we go. It says that you should be able to see my screen. Um, okay, yeah. So let's see. Maybe just to start off with a few notes, you are certainly aware there's like another one of your online exam things on Tuesday. It's all multiple choice, I think. That's what they seem to say on the Canvas, right? So, well, you've already taken one of these and I've taken zero, so you all would know better than I do what to expect. I have an idea of what type of questions usually show up on this like last exam because, I've taken it in person, uh, and I've seen like ones before that, but I don't know how they might adapt that to what you'll be taking. And I kind of skimmed through like the exam that you had, the third one, and saw the sort of questions. I looked at like a few of them. Right, so I saw like the sort of questions that you got, um, but I don't know how they'll handle this one, especially because this exam in person usually had it was usually like slightly less traditional exam because I mean you only learn like a few reactions and um a lot of the chemistry is more about like thinking about what happens in this in these sections and it's much more like application based. So typically there were a whole bunch of questions that were like draw the structure of this thing or um describe why a structure looks like this and not this. So that's usually what it was like. I have no idea what they'll do about it this time around because it's multiple choice. And there's really a limit to how many reactions that you can make somebody predict, right? So, yeah, it's kind of hard for me to tell. I'll still show you what I would normally show if you were having this exam, like typically, so that you kind of have an idea of what has historically uh, been asked and focused on. There we go. Okay. All right. So how about we start? Okay. So now you covered chapter 24, and this was on proteins. And hey, last week we talked about the same thing, right? We talked mostly about like the first half of this chapter, and the second half doesn't really have a whole lot going for it either. So, I think in this section, the main thing that was really covered was protein synthesis. Uh, so yeah, we mainly talked about synthesis in this part, and this is usually done by having like, so you could do this on solid phase, meaning that what you do is you take this thing, which is styrene, and then you add like 5% or some small percent of uh, paramethylchlorostyrene, this thing, okay, and then it makes a resin. So this polymerizes, um, because these double bonds like join together and you get a long chain. So this whole thing polymerizes and you get something that's called Merrifield resin. Okay, which it basically just makes a bead. Like that's pretty much it. It is really just a bead of plastic, but the thing is you have these chlorine groups on here, which allows you to stick amino acids on and then build up from there. So, um, the way that that looks like is you have like usually we draw the bead as like a big ball, like some large circle. I think in the book they put like a P there. Um, and then okay, we have this methyl and there's this chlorine, right? And from there we can put in an amino acid. So we put in NH2 And then here's an R group, and there's all that, right? But if we do just this, then this amino group is going to attack there, and we're just going to be left with this CO2H group hanging off the end, the carboxyl. But the carboxyl isn't very reactive. It's really hard to do chemistry on this end. So instead of doing that, what we do is we protect this amino group with one of two things. So here we can put either FMOC. Maybe let me give myself more room. Oh, I learned how to do this early. Wait. I might be getting too advanced in my Photoshop ability. Oh yeah, okay, all right, never mind. No, we're still within my skill set. Okay, here we go. So, I want to. Boy. Okay, all right, there we go. All right, so then we protect this end group, so we can use either FMOC or we could use BOC on this end, and then that means that here this carboxyl will attack instead, which is what we want, because that way we get this bead. There's that carbon, okay. That, and then, okay, there's our NH, and then there's our protecting group. Okay. So from there we can deprotect, and this step will vary based on whether you're using FMOC or BOC. We can deprotect, and then we can, add an amino acid. So a protected amino acid. And then 2 from there, okay, we can couple those 2 amino acids together. And we could do that with DCC, which we've seen before, but we'll see it again today. So we couple with DCC, okay, and there we go. Now we have our bead, 1 amino acid, another amino acid, and then a protecting group. All right, so we just deprotect. We deprotect it again. We add a new protected amino acid, stick it on the end with the coupling, and then go on and on and on. Okay. So this is a really nice way to make long proteins, like long pieces of protein. You can't go too long because like real proteins are like hundreds of amino acids long. Like the average protein is like 300 amino acids or something, right? And this method won't really get you that far because, like, you start out with, let's say, a couple million like starting pieces, right? Like a couple million amino acids start off, right? And then every time you lose like 5% or something because it just doesn't work. Something fails, there's some side reaction, whatever, right? So as you go on, you get like more and more amino acid like syntheses that fail somewhere, so you only get some amount of final product that's really actually what you want.
Can I
So
ask a
there's a
quick
limit
question?
to, yeah.
Sorry. When the amino acid attacks the resin, is it the carbonyl oxygen or the other oxygen that's attacking it? Or do we need to
Yeah.
know that?
Um, so in reality, it could be either. Um, yeah, I was thinking about this earlier, and like, I guess here there's this hydrogen, but like, usually it's really just like you can find it as an anion, and then this is just resonating.
Hmm.
So like this oxygen and this oxygen are kind of the same thing. Uh,
Okay.
we just draw them differently. So in
Oh,
this case, I left the hydrogen on the amino acid, but like it can often be off, especially because this is an amino acid. Um, it's usually found in like what's called the Zwitter ionic form. So I guess
right.
typically we have a minus charge over here, and there could be a plus charge over here, but the fact that there's this FMOC or BOC might change the chemistry. So I'll just leave this alone.
Okay.
But here we would usually probably have a negative charge, in which case uh, these two oxygens resonate. So it's neither one of them is like the one with the double bond or the one with the single bond and the charge.
Gotcha.
Uh, they're kind of both like the ones with 1.5 bonds.
Okay, thank you.
Um, um, yeah, they attach, and then we have this protecting group on the end. Deprotect. You add your new amino acid that's protected, and you couple the two, and then you deprotect it. Go over and over and over. Um, and then at the end, you can just hit it with hydrofluoric acid, which which detaches the amino acid, or I guess I should say at this point the peptide chain, from the support. And there you go. Like that's then you have your final product and you're done. Um, yeah. So that is kind of the biggest thing that you learned in this section. There are like examples of how you can actually do this. And detaching the protecting group varies between which one you use. So there are two protecting groups. So you can use either FMOC, which if you have some amino acid, it'll look like, um, let's see, it'll be a phenyl group like that. There we go. Okay. So there's like the structure of FMOC. Uh, it is particularly this whole thing is FMOC in blue. Um, so FMOC Cl is just this whole thing in blue with a chlorine there, so it's like an acyl chloride or acid chloride. And we can detach this by using, oops, so we can use this base, which is called piperidine, and this is done in dimethylformamide DMF. Okay, so then we get just NH2, we get this, and then there is also the FMOC thing that comes off, which I can't remember exactly the structure of, but uh, some FMOC thing over there on the end. Um, yeah, so that's how you get rid of FMOC, and then okay, there's also BOC, which I don't think the textbook mentions, but like you need to know it. Um, so you can use either BOC CL or Bach2O. You can imagine they're both pretty similar. BoxCl is just the acid chloride. Bach2O is the anhydride. So this one over here is that structure. Let's see, if I'm not mistaken. Um, yeah, let me just Google it real quick and check. Oh, there's an oxygen that I missed. Okay, yeah. All right, there we go. Okay, there's an oxygen, and Bach2O is if we just have two terbutyls on either side of an anhydride. So either one of these works. I think Bach2O is like the one that's most commonly used in labs, I think. That's what they made it seem like when I took the class at least. So this is one that like has come up a bunch. They've made people draw the structure of this before, so uh, it's good to know what it looks like. And then you can, I'm not gonna draw this whole thing again, like how you deprotect, but you can deprotect using uh, it's trifluoroacetic acid. So how about I draw it? Uh, yeah, so you can deprotect with.
I'm sorry. Could whoever's typing mute their keyboard?
Oh yeah. Um, okay, maybe I muted somebody. Maybe that helps. Okay, here we go. So yeah, you could deprotect Bach using this trifluoroacetic acid. Okay, and that's pretty much it. I mean, there's not much more for me to say about all this without like just repeating myself or whatever. It's better to just show a couple of examples. I guess before I do though, I'll go through like a little bit of a review of what you've seen in the past two chapters, just to like go back through and see what you've learned. Um, and I'll try to like mention the parts that are fairly important. Okay, so here we go. Let's see. There are. How would I make like a table? Maybe that's a little advanced here. Uh, so there are some concepts that you've learned, and then here's chapter 23 and 24. Okay, and then there's some reactions. Okay, so I'll always start with 23. There were a couple of concepts you learned. Um, Two big ones. So you learned how to go from like the Fisher projection of a sugar and draw it as a chair conformation. Okay. This is like an important skill. I would not be surprised if this showed up as a question. I guess I could see how it could be asked in multiple choice because it's like just tricky to be able to go back and forth between the two. So this is a good skill to keep in mind. Um, when you do this, you want to go really step by step. Take it one step at a time. Only flip two things. Don't go crazy with trying to just like go from the Fisher conformation immediately to the chair because it's a complicated thing to do. Okay, and then you also learned about anomers, which uh, I guess it doesn't seem like a really crazy concept. Like one of the OHs could be pointing up, the other one could be pointing down. Um, Not like super revolutionary, but it's good to like think about why you get anomers or like why different anomers could be stable. Um, Hopefully he talked about this in the lecture recording. I know it's come up in the past, so that's why I'm bringing it up. Um, there are just some reasons about like why you get this so-called anomeric effect where things can be going either up or down, um, which has to do with like the stability of the different positions. So, um, it's hard to explain necessarily because like a lot of the explanations that are given are kind of hand wavy, but I would just go back and check and look at like what the anomeric effect is, why it happens, like what are some rough explanations of it. Okay. So, well, you learned about anomers, and then let's see. Any other big concepts for chapter 23? I'm not too sure. Um, I think there was, I think in chapter 23, yeah, I'm pretty sure in this chapter they talked about like a little bit about nucleic acids. So maybe that's sort of a thing to consider. I don't think you need to know like the structures of nucleic acids. I mean, maybe double check me on that, but I don't think you need to know the structures of them. You should be able to recognize that they're all resonant. So like all of the bases in your DNA are have resonance structures that are aromatic. So uh, yeah, they're aromatic bases, which is kind of like an important thing to. It's an important like fact, and it contributes a lot to like biochemistry things. All right, whatever. We learned some reactions from there. So you could do oxidations. So you could use bromine water, which will oxidize just an aldehyde, and it'll oxidize it to an acid. That's because aldehydes are pretty easy to oxidize, and these are pretty mild conditions. So that'll go from just aldehyde to an acid. But then we also have a harsher oxidation, which is nitric acid. So that'll react both the aldehyde and the primary alcohol that's at the other end into acids. So this will react two things into acids, which is like, I don't know, I guess also a kind of useful reaction. And then you also have the Tollens test, and this will test for reducing sugars. Okay, so just remember, reducing sugars are ones which are hemiacetals. So, the reducing sugars are hemiacetals. That means at that anomeric carbon, there's an OH, not an ether. And then non-reducing sugars are full acetals. So the Tollens test is just a way to check for that. I don't know, like, kind of neat, I guess. It's like a cool reaction to do in person, I guess. You can alkylate or acylate your sugar, and that's just by adding like a whole ton of methyl iodide or like acetic anhydride or uh, acetic chloride. One of those things, you just add a whole bunch of it, and it'll either alkylate like like methylate or whatever all of your alcohols, or it'll acylate all of them. So it'll put like an acetyl group on all of them or something. Straightforward reaction, but it shows up. There's the rough degradation, which takes off the top um, carbon. So if the top carbon is like an aldehyde, then the rough degradation will pull it off and reduce by one. So you can go from, let's say, like a 6 carbon sugar, maybe like glucose, and cut it down to a 5 carbon sugar, which I don't know the names of. Um, I guess on that note, I know Professor Smith has talked before about like needing to know the names of the different sugars. I can't remember exactly which ones he's talked about, so it'll be good to go back through and check which ones he says that you should remember the names of. Um, there's like a whole bunch of them, and they're all like epimers of each other, meaning that like the stereochemistry at just one of the carbons is flipped. So I guess it can get kind of complicated to remember all of them. Uh, but he says that you should remember like a few of them. At least he has in the past. So double check which ones those are and maybe look into that. All right, and then there was just one last reaction, which is the Kalani-Fisher synthesis, and that's to add a carbon. Uh, so you just add a carbon onto your chain at the aldehyde position, and you do that by uh, adding a nitrile and then reducing that nitrile and turning it into a carbonyl, so it becomes an aldehyde. It is pretty much just no. I guess I can't say it's reductive amination. No, it's adding a nitrile and then reducing it. Uh, yeah, it is. So okay, all right. Chapter 24. What are the like big concepts? Well, you use a lot of protecting groups. Okay, Bach and FMOC, and I guess that kind of falls under peptide synthesis. Okay. This idea of peptide synthesis, where you're like doing something on solid phase, is a pretty important idea in chemistry. So, uh, yeah, it's naturally one that is kind of asked about a lot. And then in terms of reactions, what reactions have we actually seen? Uh, well, let's see. There are like a there was kind of like a review of different ways to synthesize amino acids. So in terms of synthesis, you can do reductive amination, right? So you are just uh, directly making a an amino group, an NH2, on there, and you're doing it by using usually like an alpha keto acid is kind of the way you do reductive amination. Okay, so that's one way you could do it. Second way, you can do the Helvohard-Zelinsky reaction on a carboxylic acid, and then from there you can do just like plain SN2. So you add excess ammonia, and it'll kick off that bromine that you got there. And then number three, you could do the Strecker synthesis. Okay, and this one winds up being that you put a nitrile onto I think like an acid, right? And then you wind up reducing that nitrile. Um, and that should become an amino group. No, I think it might become an acid. Uh, yeah, I can't remember all the details off the top of my head, but that's like the last way that we've commonly seen to make amino acids. And these are convenient because they let you make whatever side chains that you want also, right? So like there are 20 or really primarily 20 naturally occurring amino acids. Well, this lets you make hundreds of thousands of different types of amino acids. You can make whatever one you want. You can put it in an organism and you can make it do like interesting or neat or cool things. Um, yeah, there's a bunch of cool stuff that you could do with unnatural amino acids. I won't get into it too much, but like one really famous example is something called click chemistry, where you can put like uh, a side chain that has a triple bond on it, and then that triple bond is able to react under really mild conditions with like a fluorophore, something that lights up. So that way you could do click chemistry. It's called click chemistry, and you could do it on an amino acid that you've introduced unnaturally, and then wherever that protein is, it'll glow because you've just stuck a fluorophore on there with a covalent bond. So All right. Anyway, okay, whatever. That's enough biochemistry. This isn't that class. So, all right. So you learned a couple ways of doing synthesis, and then you talked about reactions that you can do, uh, that you could do with proteins. Okay. So one of them, I only put this because the textbook included it, and you always, always, always need to know how to do Fischer esterification. So hey, it's a good reminder, I guess. Okay. Uh, the fact that it's an amino acid and it has that carboxyl group on the end, that just immediately means you could do Fischer esterification. So obviously the book is going to include it. Um, and it's, it is a relevant reaction. Okay. Uh, so let's see. Uh, you can make amides. And this is with DCC. This is DCC coupling. This doesn't necessarily have to be with amino acids. You just need an NH2 and you need a carboxylic acid. You can stick those together with DCC however you like. All right. Let's see. You also learned about the reaction with ninhydrin, which has like this whole structure, and I don't even think you really talk about the mechanism very much. Maybe I'm misremembering. But you should know the structure of ninhydrin, and you should know the products that come out at the end. That is very much a question that's been asked, and it's like a little bit silly because you could just memorize the structure of ninhydrin and memorize the products. But I mean, hey, like it's a free point, I guess, right? Uh, as long as you just memorize like what the structure is. I can't say for sure once again that like they'll ask about it this time because I have no clue. It's a whole different format and structure, but it's come up before and they like asking about it because it was like I think it was developed in Penn's chemistry department. So, go Penn, right? Uh, there is the Edman degradation, which uses a special reagent. So it uses pH NCS, phenyl isocyanate, or something like that. I can't remember the name of it. Um, Isothiocyanate. That's it. Okay, whatever. Yeah, so this reaction, it gives you a very particular product as well. Also, probably just one of those ones where you can just remember the product, and if it shows up, then hey, nice, you know exactly what the product is going to be, right? Uh, yeah, and then the last thing you learned was solid phase peptides. Okay, we've already talked about that. All right, so yeah, these are the concepts and the reactions that you've learned for these two chapters. Um, I've made long lists out of them, but like if you kind of like look at it carefully and think about what on these lists is actually new, there's not that much. You've learned like maybe 3 or 4 new reactions between these in each of these two chapters. So not a whole ton of reactions to talk about. It's more just like looking at what you can actually do them on because peptides and sugars can get pretty complicated. All right. Well, how about in that case, how about I save this document? Make a new folder and save this. And I will make a new one. So we actually start answering questions. Here we go. This is the slow part of every one of these workshops. Okay, all right. And paste. Here we go. Oh, look, it's a bit too big. That's okay. All right. Well, this is a mechanism question, which, everybody loves. So, okay, here we go. Draw a detailed mechanism for this transformation, and we could see there's an there's a carboxylic acid, there's an amine, and we're coupling with DCC. Okay, so we're getting this amide out, and then here's this garbage that comes out at the end that's called DCU. Like I don't even remember what DCU stands for. Okay, this is DCU. All right, whatever. So okay, then let's just go in and write out the mechanism. Right? We know exactly what we're making. Uh, we know what we're doing with. So here we go. Okay. So we start off with our acid, and we have this DCC here. We have to know the structure of DCC though, so let's pray that I get it right. Whoops, there's another N there. There we go. Okay. Hopefully I got that right. If not, anybody could correct me, but I think that's good. Yeah?
Yep.
There we go. Okay. I still got it. Okay. Uh, so here we go. This is an acid, and these two nitrogens are like kind of basic. Remember, they're imines, so imines are still sort of basic. Okay. So here we go. We're just gonna grab that H off there. Okay. This is equilibrium as far as I'm concerned, right? So here we go. We get the anion, and over here, I'm just gonna draw these circles for the hexagons because it kind of speeds things up. Okay, and there we go. Now we have this structure over here. Fortunately, there's no like additional junk over here because it makes it kind of faster to work through this problem. So, all right, here we go. We get this oxygen. How about I use my electron colors? There we go. This oxygen will go up there. Okay, we get some bonds moving around over here. And okay, so this will attack onto there. Let's see. Let's draw this whole structure. So we have this carbon, and then an NH, and this whole thing. Right, we have this N over here, and all that. And now we've added this, oops, this structure hanging off the end there. All right, so we have all this over here, and now we want to introduce this NH, this methylamine that we have over here. Okay? So, well, let's see. If we take our NH2 and we take the electrons that are here, we throw this off, then that means these electrons are going to go to that oxygen, or I guess really they'll go over here to that double bond, to make a double bond, and then now these electrons are going to go somewhere. But, well, they could go to that nitrogen over here, but maybe this will happen a little bit. Well, then we'd get a minus charge on a nitrogen, and that's kind of usually weird to have. So where are these electrons from this double bond going to go? Okay, so we know at the end that we want this carbonyl here, and we want NH on either side. So all we need to do is get a hydrogen onto here. So where can we pull a hydrogen from?
You just take it from the MENH2.
Yeah, so we can actually just grab it from over here. Okay. Yeah. So that's what we can do. And then, all right, from there, uh, this one's not really equilibrium because once we have this DCU structure at the end, this is pretty stable. Um, or at least the reaction's not going to go backwards at this point, really. So, okay. So then we have, uh, we've added our methylamine there. And from there, we had this C, and we made a double bond to the O. We have an NH with that that hexagon at the end, the cyclohexane, right? And then over here, we also have, we made an NH, and bam, there we go. So that would get us our product. That's it. Um, this happened like a lot in one step. So, you can break this down into multiple steps so that it would be like maybe, let's see, how would we do it? Maybe like this, and then you could do probably something like this and have this NH3 with a plus charge over here. So then, well, this is going to reform that carbonyl, and then these electrons are going to hop over, which will push this bond to grab that that hydrogen. So okay, well that's pretty much like the same mechanism. Maybe it's just a little bit cleaner because we already attached this NH2 onto there. Whoops, this should be an NH2, shouldn't it? Yeah. Okay, so it's maybe like we cut down on one arrow or something. Uh, but the chemistry going on is still the same. Okay. Okay. So that's, yeah, there we go. We got our final product there. Um, this is just like a common reaction, and it's very fortunate that it's so nice because like you would expect that such a useful reaction might get like, I don't know, more ugly or something, but well, no, it's not so bad in terms of the mechanism, which is a big plus. Whoa, whoops. Okay, here we go. Let's paste and add the next problem. Here we go. Okay. So we have this fairly interesting looking peptide, and we're getting this weird product at the end. Um, so the reaction that we're doing here might not be immediately obvious. Um, in fact, it's kind of weird, but this product should signal what reaction mechanism we're following. So, does anybody know what reaction we get this product from?
The Edmond degradation.
Yeah, there we go. So this is an Edmond degradation. Yep. It's just that we've already done the first step for you, right? Here is this. This is this pH NCS, right? It's just been attached to our peptide now. Okay. So let's see. How should we go about this? Let's say we
Were
have.
you responsible for the mechanism of this? Because I'm pretty sure the TAs, if I remember correctly, you're saying that we don't need to know it, but what
Oh,
are
you
your
don't.
thoughts? What are your, I mean, maybe it's safe to know it.
Um, Yeah, I guess thinking about it, so when I was looking back through, I don't think I saw any particular places where they asked for the mechanism, actually. Now that I think about it, yeah. Um, I know that you're expected to know what the product is. That is,
Yeah, yeah, that makes sense.
that one's for sure.
Yes.
Um, yeah, I guess I haven't seen where they asked for the mechanism of it. And oh, yeah, no, yeah, I don't think so. I'm trying to think back. Um, there, that could have to do with like I was looking for the full mechanism of this thing because even in the book, I know it says like, oh, you go this amount and then you get this product, right? And they show you how to get there. And then it does this conversion and you don't need to worry about how it happens, right? So I was looking around for like the actual mechanism behind that conversion and uh, I mean, I found some stuff, but it seems fairly complicated. So how about I put it here, and then maybe we won't worry about it. We won't worry about it so much because you might not fully need the mechanism. Um, yeah. So okay, here we go. How about from here we have uh, we need to somehow make like a ring structure out of all this stuff, which is a little complicated, but it goes through this interesting mechanism where here we have, oops, not there. So this NH will make a double bond over here, which will send the electrons that are on this sulfur over to here. Okay. So from there we have, oh, let's see, this is a bit complicated, right? So we have this N, the sulfur, which goes to this carbon, which put an oxygen over here. Okay. And then, let's see, hanging off this sulfur, we have this carbon, and then there's an NH, another carbon up here, and then that carbon, the carbon with the oxygen there. Okay, and let's see, we're probably missing some stuff. So this carbon over here should also have this NH with peptide, right? Yeah. So we have that. Um, and let's see, am I missing something on this chain? I guess usually there would be an R group there. That's sort of the thing that is throwing me off. But we're working with an amino acid that has no R group, which I guess makes it a little bit weird to look at, but it should still hold up the same. Okay. Uh, just for fun, this amino acid with no R group is called glycine. So glycine. Yeah.
I
Okay.
think you're
And then
missing
from
a
there,
nitrogen in the ring.
huh?
Oh, sorry. No, one of the
Oh,
products has like two nitrogens in it. It's like, where'd they go?
yeah. Here we go. Yeah, I missed that. So there's a pH, this NH, right? That's hanging off. That would probably be it. Yeah. Thing that's missing. This OH becomes, or sorry, this O minus becomes an OH, and then uh, from there, that OH a C double bond O. So from there we get this structure, and it kicks off our peptide. Okay. So this should be the structure that we're kind of left with right now. Um, I think this H that's here also comes off, and you wind up getting a double bond between the carbon and nitrogen. But, well, we won't worry about that too much. Um, okay, cool. So we get this structure now, and through some magic, according to the book, you add acid, and from there, it changes and it becomes something else. So it becomes instead. Now I'm just redrawing the structure that's up here because uh, the actual mechanism for it isn't explained anywhere. It just like apparently happens when you introduce this acid, right? So the structure winds up becoming something like this. Did I get it right? Oh, okay. Looks like this. All right. Well, whoops. Okay. Well, where did this come from? It's not explained anywhere. I went and I found like an actual diagram that shows the mechanism. So how about I like add it here and then we'll just look at it for like, a small amount of time and then otherwise not worry about it so much. Okay, so here's what it looks like. Um, we've seen this structure, right? We know what this one looks like, and then, oh boy, this is kind of complicated, right? Yeah. Um, I didn't actually look at this too carefully, and I didn't realize, like, wow, okay, there's so much going on here. So it looks like it involves a whole bunch of like protonating and deprotonating, uh, and you split the ring open. So I guess you get this C double bond S back again, and you also make this acid here. But what it winds up coming down to is just the fact that like, see, you I think pretty much just swap out these two bonds more or less, right? It's certainly more sophisticated than that, but if you just swap out those two bonds, I think everything else is pretty much exactly the same, right? Yeah. So you could think about it like that. That's like the really, uh, lazy and fast way to think about it. Um, if you're nuts, you can go through this whole mechanism, but I don't think that they expect you to. And this is like, I had to pull this from online. I didn't see it mentioned in the book, or I don't think it's talked about in lecture for sure. Uh, so this is like, I don't know, optional, not needed. Yeah. I sincerely doubt that they would expect you to write out this mechanism. All right, well, okay, that's probably enough talking about this reaction. Um, let me pull up. Whoops, I want to go here. All right, let me pull up something new so that we don't have to talk about that hideous reaction anymore. Please. Okay. This question is like actually pretty relevant. Okay. This is the kind of one that like at least uh under usual circumstances would show up. This is the sort of thing that like you can expect uh to be an important question because it's about the solid synthesis of an amino acid. So it's kind of important, right? So here we go. We have this bead. So I'm going to call this whole thing P because this styrene, this like phenyl ring doesn't really do anything for our reaction. We don't really use it, right? So here we have this PCl, and now we want to make phenylalanine and alanine, okay? that's these two structures drawn here. So this is alanine and this is phenylalanine. Okay. Notice phenylalanine is just alanine, but with this phenyl group. So uh, this is like the most rationally named amino acid that there is. All right, so we want this to be the N terminus, and we want the C terminus over here. Okay. And maybe does anybody want to remind me, this solid phase peptide synthesis, do we build from N to C or C to N?
C to N.
Okay, so it's C to N. Yeah, in fact, that's right because at the start we attached the C terminus. Remember, that was kind of like the important feature, right? Meaning we want to start with alanine. So and then 2, we want to attach phenylalanine. Okay. So then, well, we might as well get to it, right? We have this structure, which we know is alanine. Okay. And so it's got this carboxyl group up top. There's a side chain, and then there's this NH Bach. Okay? And this NH is protected, so it's not really nucleophilic, meaning that this carbonyl is going to be the most nucleophilic thing we have. So, all right, it's going to go and anchor itself. Okay? And we lose that chlorine, and it's gone.
I have a
So, okay.
question.
Yes.
Are we always assuming that we're at a pH of 7? So, like, how do you know
Ah.
when the carboxyl group is protonated or not?
Yeah, I guess. So we, unless otherwise specified, we can probably assume that we're at pH 7. When you have an amino acid in general, maybe let me put a box. So, uh, so in general, when we have an amino acid, we have usually NH3, and then we have this carboxyl group. And so this has the NH3 group gets deprotonated at a pH of about 9. I guess it's usually like 10. Whatever, close enough. And then this will usually be deprotonated or it'll get protonated at a pH of like 2. So we can pretty much always expect that this carboxyl group is going to be deprotonated. But this is for a regular amino acid. Here we have it protected. So the effect of this NH group is probably going to be reduced. In other words, this carboxylic acid might be a little bit less acidic than we would expect it to be normally. What that means exactly for like this reaction, whether it's protonated or deprotonated, I'm not 100% sure. Because normally having this NH3 plus stabilizes this minus charge on the carboxylic acid. But here we don't have that NH, like the positive charge over here. So this would be less acidic. I would say probably it's still going to be acidic enough that if it's just at pH 7, like just in regular water, it's still going to be, it's still probably going to be deprotonated. The reason I say that is because the C terminus of amino acids of peptides is usually deprotonated in whole proteins as well. And whole proteins are pretty much just like, this carboxyl group and this NH with stuff on the end. So this NH usually isn't protonated in whole proteins, but this carboxyl group is usually still deprotonated. I can't remember the exact pH that happens at, but in pH 7, amino acids will probably be deprotonated, even when protected. Are there any other questions? Because this is like a sort of weird point, I guess. It's a little bit flexible too on whether we say there's a proton on there or not, just because like we're kind of working with pHs or pKa's really, where we can go back or forth between the two kind of leniently. All right, how about I continue with the mechanism then? So, all right, we're attaching at this carbonyl, right? So, okay, there's that carbon that's left over, make sure not to lose that. And we're attaching there. Okay, so we have carbonyl. Next carbon over, we have this methyl group, because this is alanine, right? And then we have our NH with Bach. Okay, and just a reminder, because, well, it's good to remember. So Bach is this thing. Okay. So like maybe I should say like R Bach is there's an R there. Okay. Just a good structure to remember often. All right, so we've attached our amino acid to our support, and well, it's protected, so we can't really do anything with that. So let's deprotect. And with Bach, what should we use to deprotect?
TFA.
Yeah. So you can use TFA, which is trifluoroacetic acid. Okay, so that's CF3, and then a carboxylic acid. Okay, so all right, well, say goodbye to Bach, and there we go. Now we have an NH2, and this thing is like gonna go wild. Okay, it can react a whole bunch and do some interesting stuff. So now we want to add our next thing. Okay, so we've synthesized alanine, but now we want to add phenylalanine onto this N terminus. Okay, great. So the other thing that we're given over here was this phenylalanine that has Bach on it. Okay, kind of helpful. We need that, right? So here's this amino acid that they gave us. Okay, looks like this in a very small space. Okay, so there's that amino acid they gave us that's protected. Okay, but these two aren't going to attach to each other just like that. So what else should we add?
DCC.
Yeah, exactly. So we'll add DCC there. And fortunately, this question doesn't care about mechanisms at all, so it just adds it together. And we don't have to worry too much about exactly how. Okay, so we made an amide, and then we've attached the rest of our amino acid. Okay, so this is close to it. So we have alanine, and over here we have PHE. But over on this end we have this resin, and over on this end we have Bach. Okay, so how are we going to get rid of the Bach? Well, okay, I've already asked you that question, so maybe I'll just skip that one. So now we have this bead, we have alanine, and we have phenylalanine, and over here there's this OH. Okay, and now how do we get rid of that bead? Final step.
HF.
There we go, HF, and there's NH2, there's alanine. Oh, whoa, whoa, whoa. No, there isn't. Okay. There's NH2 on this end. And whoops, yeah, missed that. So over on this end, there's a COOH. There's an alanine. There's a phenylalanine. And then over here, there's an NH2. Okay. So from N to C, we have phenylalanine, then alanine. Okay. And well, this problem was asking for from N to C, we want phenylalanine to alanine. Okay, so we did it. We got it. Okay. So just to go back through that, we had our resin, and we attached alanine first because this method goes from C to N in its synthesis. We add our alanine first. There we go. It's protected. It's on the resin. It's not going to do anything like this, so we deprotect it with TFA for Bach. Okay. We add our new amino acid and couple with DCC. So, okay, nice. Now we have our two amino acids connected, and it's just a matter of deprotecting. So we add TFA to deprotect, that is, to get rid of the Bach, and then we add HF, and that takes it off the bead. So now we have our final peptide, which is, two amino acids, so it's a modest start, but, well, it works. Okay. How about I save this? And any questions on this process?
Could you explain how this is different from solution phase?
Two
Sorry.
people. How it's different from what? Sorry.
From solution phase?
Yeah, so if I remember correctly, solution phase happens from N terminus to C terminus, right? Yeah, I haven't seen solution phase in a while, so I don't remember it coming up anywhere. Although I know he talked about it. It's just been a while. So if I recall correctly, solution phase is from N terminus to C terminus. So that's like a drastically different change just in terms of how you think about the problem. And there's also the other fact, which I guess we don't think about so much in this class because like we're just thinking about what reaction will happen and like when. But the fact that you're doing this one on solid phase, like a bead, like something that you can hold on to, means that you lose a lot less of your product. If you're doing something in solution, then everything is floating around with everything else. So like each time you do every step, you have to purify it. And every time you purify, you lose a whole bunch. And it especially gets hard because like you have to purify peptides from other slightly shorter or slightly longer peptides. So, well, that can get kind of hard. But here, all you have to do is, okay, you add a chemical. Let's say you add, like, up in this step, you add trifluoroacetic acid, TFA, right? But it's on the peptide that you're working with is on the bead. So all you have to do is hold on to that bead and then get rid of all the liquid. And then you could just add new stuff also. That's the reason why with this is the kind of preferable method for building up larger peptides, because you can you don't lose a whole bunch every time you do it. I mean, you lose some because you get side reactions and a whole bunch of other junk can form. You can never expect the reaction to be perfect, but you hold on to a lot more, so you get much better kind of yields. Does that sort of go through your question? I guess there's more to talk about with exactly how you do solution phase peptide synthesis, which, well, I haven't seen in a while. So I can't remember exactly which protecting groups or which mechanisms you use for that. But that's kind of the conceptual difference between the two.
It does. I was just confused because he mentioned it in class, but the book doesn't really talk about it at all. So
Yeah, I don't remember him asking things about it at any point in the past. Um, Maybe it could be one of those few points that says oh, name what chemical you might use for solution phase peptide synthesis, or explain why solid phase peptide synthesis might be preferred to solution phase peptide synthesis. But then again, your exam is multiple choice, right? So there's not going to be any of these parts where you have to write and explain something. Probably, right? Yeah, so I'm not sure.
thank you.
Okay, there was another question too.
Oh, yeah. I just wanted to make sure. So we can assume that the carboxylic acid will always be deprotonated?
Yeah, it's probably safe to say that, yeah. Um, yeah, I'm trying to think back to because this is something that's talked about a whole ton in any biochemistry class that you'll take. Well, I can't say any, but in the biochemistry classes that I've taken, it is talked about a whole bunch because there's there's a number of effects that happen in amino acids, which is the fact that you have this NH3 and this carboxylic acid so close to each other that makes both the amine more basic and it makes the acid more acidic. So it has to do with the fact that well, first off, you have a plus and a minus charge right near each other, which is that's already pretty nice, right? You generally like to have pluses and minuses next to each other. But there's also other effects going on. This I think this NH3 is inductively withdrawing, so this acid becomes more acidic, right? Because you have a withdrawing group. So acids tend to become more acidic inductively, right? But this carboxyl, I think, is also a withdrawing group. And oh boy. No, I don't think that makes the amine more basic, but there's also an effect from the carboxyl group, which probably has to do with the resonance structure and the fact that these oxygens are both pretty partially negative, so that stabilizes this positive charge over here. The point is that this carboxyl group is a lot more acidic than you would normally expect. So in general at pH 7, or really at anywhere from pH 10 to 2, you can expect an amino acid to look like this. Earlier it was a little weird because you don't have that positive charge on this end, this nitrogen, since it's protected. But, well, you still have some of those other effects, right? For example, this is still inductively withdrawing, meaning this carboxylic acid will still be a bit more acidic. Yeah, there's some other effects at play here. I can't remember all of them. They get a bit more complicated. But the idea is that generally you can assume that this amino acid will be deprotonated. Yeah. To answer your question short, yeah, you can probably just assume that it will be deprotonated.
Okay, thank you.
Yep. save this and I'm gonna make a new file. All right, and let me add a new question. Here we go. So these are some predict the product questions. I kind of mentioned like a while earlier that, well, there isn't that much predict the producting here, right? You have only seen a few reactions in these chapters, and so there's only so much you can do. That being said, they will bring in a whole bunch of reactions from previous chapters. Okay, things like adding an amine or doing reactions with amines, those can very well show up because proteins and sugars, they have amines, they have aldehydes and ketones and all of that. Okay, so those reactions are like, well, they're good to keep in the back of your mind because they can show up and there's not too much else to ask about. So it's very probable and possible that they'll pull from things that you've seen in the past. All right, well, here we go. We have ethanol and acid, and we have this sugar that we're putting in these conditions. Okay. Exactly what this sugar is, I don't remember, right? We have equatorial, oh, and then there's an axial something over here, right? And so it's an epimer of glucose, but, well, who knows? Okay. No, this is also let's see, this is like what, the beta sugar? Anybody want to correct me if I'm wrong? I think there's some mnemonic for it. Is it like alpha goes above?
Alpha's
Or is
below.
So alpha's below.
Yeah.
Oh, okay. So it's one of those backward mnemonics, right? Like, it's A for alpha, so you would think it's above, but no, it's actually below. All right, so this is an alpha sugar then. Thank you. Cool. So, all right, I guess that's what we can say about it. It's also an aldose, right? Because this anomeric carbon has an OH, or really, it's a hemiacetal. Okay, so this came from an aldehyde at this end. All right, well, whatever. That's all good practice. That's not what the question's asking for, though. Okay, so we put this sugar into ethanol and acid. So what are we going to produce instead of this sugar?
Are we just going to replace all of the H's on the hydroxyl groups with ethyl groups? Or, yeah. Or no?
So we could, but this alcohol plus an alcohol isn't going to react very much. There are these sort of like what are called bimolecular condensation reactions where you take an alcohol plus an alcohol and it gives you an ether. But in this case, there's not going to be much of a way for this ethanol to kick off these OHs. That's sort of a weird reaction to happen. Does anybody else have any thoughts about what we might do?
You're gonna get like a glycoside, and it's just gonna be the anomeric carbon that reacts, right?
Yeah, okay. So what happens is, well, first off, we lose stereochemistry here, right? That'll happen pretty much whenever. Whenever we put our sugar into acid, then okay, we get anomers, right? So we draw that with the squiggly line, and instead of having an OH, then now we have an OET. Okay, so we've gone here from hemiacetal to acetal. And the rest of these will stay as just alcohols. Okay? And maybe more importantly for this section about sugars, if we're going from hemiacetal to acetal, that means we're going from a what sugar to a what sugar?
Reducing to non-reducing.
Yeah, there we go. Okay. Meaning that this first one will react with the Tollens reagent, the second one won't. I don't know if that's too like mind-blowing or life-changing, but okay, well that's something that has changed between these two sugars. Okay. Exactly like how this actually happens is it involves opening up this ring. So okay, well we get equilibrium, whatever, right? So this ring will open up. So we can get like these electrons coming down and kicking this off, provided that okay, this hydrogen, this oxygen is protonated. Okay, whoops, not like that. Oh, this is really ugly. All right, let me redraw. So okay, it will look like this. Okay, we can decorate it with all of these OHs. And then over here we have this aldehyde. Okay, I got rid of this extra hydrogen that's hanging off there, which is just going back and forth, doing a bunch of these proton transfer steps, right? We're in acidic solution, so we're just swapping hydrogens around back and forth. Okay? And then now we have, well, actually, let's keep this protonated, why don't we? Now we have this ethanol. Whoa. There we go. Okay, so this ethanol will remain an attack here. Okay. I'll skip drawing all these extra OHs because we're not too worried about those. All right. So now this guy over here will get, well, it'll get protonated and become water. So it'll just take that proton off the next thing over. And then some electrons will hop down from over there, and that water will just come off. Okay. Now we'll have, I think, probably something that looks like this. Right, and now, okay, this alcohol is going to go back and attack him. Okay, so this gives the product, which is what we drew above. That's why only that anomeric alcohol changes or swaps out. Okay. This reaction, I'm trying to think about it. There might be like a slightly more clean way of writing out this reaction. But this one works. And the main point is that this we just get the anomeric carbon that gets swapped out. That's all. All right. How about I put in the next problem? here we go. So, all right, we have this structure over here, which is like something. We've seen it before. I can't remember the name of it. I think it's like malonic acid, right? Hopefully, yeah, I think so. Okay, so we put it in base. We give it 1 iota butane, and then we put it in acid. All right, so how about we do step 1? So we put it in base. So what's going to happen to this structure over here?
Deprotonate the carbon between each of the, I guess, esters.
Yeah, exactly. Okay. Remember, so the pH of this carbon in the middle is something like, or the pKa of this carbon in the middle is something like ridiculously low. It's super acidic. It's like pH of 9 or 10 or something along those lines. Okay. So yeah, sure. We get this minus charge over here, and now we add step 2. We add 1 iota butane. So, well, we haven't done that much naming, but this one shouldn't be so bad. So there's an iodine, and it's on this butane. Okay. So what type of reaction are we doing?
SN2.
Yeah, SN2, exactly. There we go. Right. All those months ago in Orgo 1, you were thinking this SN2 is so stupid. When am I ever going to need this? Well, here you are at the very end of this course, and you're still stuck here doing SN2 reactions. So there we go. That's what it looks like. Okay, and then we use acid and heat. Okay, so that means, well, this is like one of those particular structures, and at the end, when we heat it with acid and heat, then something happens to one of these groups, right? One of the groups will leave, and then something will happen to this other group, and we get a final product. So, okay, so we know that this group at the end, this one group on the side will leave, and then something can also happen over on this end too. Because it's so acidic, we can just remove this ester over on the end and turn it into an acid instead. So there we go. We have our 1, 2, 3, 4. This was the butane that we started with, and then over here we get an OH. Okay, so this is 1, 2, 3, 4 of butane. Okay, and then over on this end we have acetic acid. Okay. So I can't remember exactly the name of, I'm pretty sure this one was the malonic ester synthesis, right? So the point is, at the end, the product that you get is a substituted acetic acid. So that's what we got. Okay. We have this acetic acid, and we've just stuck a butane onto it. Okay. Maybe you'll notice this question doesn't have a whole lot to do with chapters 23 and 24. Really, it has to do with chapter 22, the one on these alpha keto reactions, like the substitution reactions. I can't remember what they're called right now. This is a good hint for me mildly saying that it's good to think about reviewing, because while it might not necessarily show up in the questions that you'll see in a few days, it certainly will show up later in the final. So, besides the fact that it's good to keep remembering, because like there's not a whole lot of reactions that you'll see on the test in a few days. So, besides that, it's um, still good to remember what reactions you've learned. How about I leave this up and pull up a new question? Any questions about this reaction? Whoops. Here's what's next. Okay. All right, here we go. This is drawn in Fisher projection, right? So, okay, this is a sugar problem. Hopefully, we would think so at least, right? Um, so okay, we've got something a bit more relevant now. Okay, and here we go. We're taking this structure and we're adding this formaldehyde, and it's under acidic conditions, and then we add this sodium borohydride. Okay. So what does this reaction kind of look like? What does it make you think of? So, okay, well, what can react with this phenyl or this formaldehyde? Okay.
The amine.
Yeah. So this amine could react with the formaldehyde. Okay, and it's under acidic conditions, so what are we going to form instead of that carbonyl?
Do you make an imine?
Yeah, exactly. So let's just redraw this structure. Over here we have this pH. We have these two phenols on top and bottom. Presumably they won't be involved in these reactions. But okay, now we have this. So instead of this formaldehyde, we put it with an amine in acidic conditions. So instead we wind up getting an imine. That looks like that. Okay. And then we give it sodium borohydride, which will do what to this imine?
Just reduce it.
Yeah, exactly. Okay. So we reduce it.
That actually wasn't that bad.
No, it seems like a lot more. Okay. And now we add, here we go. Now we add this hydrogen peroxide. And this is kind of weird. So hydrogen peroxide, okay, we know that it oxidizes things. So what is the only thing on this molecule that we can oxidize?
Still the nitrogen, right?
Yep, exactly. So, okay, we're going to oxidize it again. And, okay, we usually don't deal with this sort of reaction, but, well, it'll look something like this, right? Okay. And now maybe this sort of thing is looking a little bit more familiar. So does anybody remember what reaction we're doing here with this whole hydrogen peroxide and heat thing?
Is it like the cope elimination just with different reaction conditions?
Yeah. So this is the cope elimination. Um, yeah, in fact, it is exactly the coelimination, right? Um, wait. The coelimination usually needs to be done on primary amine. Yeah? Or am I misremembering?
I know we gave the Hoffman product, but like I think this is a cyclic elimination. I guess that's what you call it then.
Um,
So why do you get the oxygen on the nitrogen again? For the H2O2?
so we're oxidizing our amine. Um, and the coelimination usually produces a product that looks like this with this oxygen on here. Um, it's like a weird structure, I guess. It's kind of an unusual one. I'm trying to find exactly. Yeah, it looks like this. Okay. So okay, so this is fine. No, wait. Yeah, no, I was misremembering. Um, yeah, we can do this. Amines will, I mean, the class doesn't talk about this so much, but amines will oxidize pretty easily. So hydrogen peroxide will oxidize it into this structure over here without that much trouble. Um, I think. Oh no, no, no. So it becomes. Oh man. This structure becomes like this. Um, yeah, this product, this question's a little bit weird. Maybe it's kind of weird because like maybe we were supposed to methylate this nitrogen twice, because this is all given in one set of conditions. Although, I mean, if you put this formaldehyde and this sodium borohydride together, then well, it'll just reduce this into methanol, right? Yeah. Okay. Yeah, so when we do the coelimination, we usually want it to be a tertiary amine. So ideally, we would want something that looks like this with two methyl groups. Then we can oxidize it and do a coelimination. Um, so yeah, I'm telling you that this problem should use a coelimination. Um, that part I kind of like know, and there's nothing else that we can really do with these conditions. We haven't really worked with this very much otherwise. So how about let's say that we do this process twice and we get two methyl groups. Right? So from there we uh we oxidize it with hydrogen peroxide, and now we've got this structure. Okay, so we can do coelimination now. Um, that is an option for us. All right, and what hydrogen would this oxygen pull from? How would I label them? So there's these methyls. That's one. Over here, 2, 3, 4, and 5. So which of these hydrogens would this oxygen pull off or eliminate?
Hydrogen 2.
Okay. What makes you say hydrogen 2?
Just because that's like the only accessible one to create a double bond.
Yep. Yeah. You are entirely right. So how about I use like red? Okay. So this oxygen is gonna grab that hydrogen. This bond is gonna come over here and take off that N over there. All right. And so now we're left with, let's see. All right, now I'm going to draw this a little bit weird, but I'm just going to keep it the way that it was. Okay, so this Me and this pH. Okay. And the reason I drew it like this kind of weird way is because you can just kind of nudge the bonds over a little bit, and that way it'll look like the structure at the end. Okay. If you don't believe me about this whole thing about like nudging the bonds over, like kind of just adjusting the angles we draw them at, you could think about how you would draw this like in its like regular proper projection. So it would look like this would be coming out. This would also be coming out. Right, there's a hydrogen over here. Because these would both be going in. Well, yeah. So you can redraw this structure and think very carefully and spend a long time working out exactly what the stereochemistry will look like once you pull these off. But it is just a little bit simpler to think about like, okay, we know what the relative positions of these two are, so we can just shift it over a little bit. We know what the relative positions of these two are, so we can just adjust them a little bit too. Yeah. Yeah. This question's a little bit tough. Maybe it also involves like uh, turning this NO to be on the same side as over here. That way you get the proper stereochemistry. Yeah, I guess it probably does. So it winds up being a little bit complicated. This might be a good sort of situation to use like a modeling kit, for example, just to keep track of where all of your bonds go and what things wind up looking like at the end. But over here, the product will look like this at the end. Okay, it'll have these two phenols opposite to each other. Okay, so I guess sort of a weird problem because it involved methylating that amine twice. And, well, methylating twice with reductive amination is kind of like a weird process, right? Because we'd have to add one formaldehyde and reduce, and then add another formaldehyde and reduce. So, for the sake of this problem, I guess think about it that way, that we're doing it twice over. Although these conditions don't really indicate it that well, so maybe this problem's kind of like a little iffy. Okay. Main idea here being that we did a cope-elimination. Yeah, perhaps it would have been better if we said like, okay, use two equivalents of methyl iodide or something like that. But anyway, grab one more problem. Well, there's two more problems, but use this one in, and as usual, it covered up the problem we just did. Okay, here we go. So we have this structure. Oh boy, there's two ketones over here, and we're putting it in base. So before I even look at what the other reagent is, what are we doing?
Robinson annihilation. Well, oh, sorry. You're going to take off a hydrogen.
Well, yeah. First
Yeah.
off, yeah, we know right away for sure that we're taking off a hydrogen. I haven't even looked at the other this other thing over here. So this is methyl vinyl ketone, which, if I remember correctly, with your help of telling or indicating that this might be a Robinson annulation, uh, should look like that. Okay. So, well, you make a really good point that this probably is a Robinson annulation because here we have we're making an enolate and we have this good Michael acceptor, right? Because it has these conjugated double bonds. So it's also happening in one step. Okay, so it's, it kind of looks like it'll be a good Robinson annulation. Then, well, let's do that. We know Robinson annulation is always there's always two steps. One, do a Michael addition. And then two, well, from there we usually do a oh, did I draw methyl vinyl ketone? I think it looks like this, is it? Yeah, I think it is. Okay. So we do a Michael addition, and then from there we make an enolate and we attack back at a carbonyl. So the second step would just be like a I don't know, alpha keto nucleophilic attack. The name for it is escaping me. I'm doing real bad with names today, unfortunately. Okay, but that's the main idea with this Robinson annulation. So okay, we have our Michael donor because this is a very good enolate. And all right, well, let's give it our Michael donor. There we go. It'll go over there, move up to there. So let's redraw it to take this all one step at a time. Okay, so here's the carbon that we were at the base with, and then now we get that carbon there, a double bond. That oxygen is up here from that double bond, and there we go. All right, and now we do keto-enol. Just because we have this enolate and, well, we usually prefer to have a ketone than an enol, so we do keto-enol tautomerization. So, okay, there we go. We have this ketone, right? Yet, we're still in base, so we can either deprotonate over here or over here. Which one are we going to pick, one or two?
Two.
Why two?
It's a more acidic hydrogen, right?
Oh, is it? We'd wind up getting. Oh, well, yeah. Well, yeah, you're right. Yeah, I was thinking of cations, right? We'd have a carboanion on this primary carbon, which, okay, that's already more favorable than over here, right? There's already one reason why 2 is better than 1. Is there any other reason why we would choose 2 over 1?
It's going to end up making a larger ring in the final product.
Yeah, exactly. If we choose carbon 2, then we'll get a 6-membered ring, which, well, we'll see that it comes out to be 6 in just a moment. If we chose carbon 1, we would have to make like a 4-carbon ring, probably. And we generally can't do that with like Michael additions like this. We can really usually just make 5 or 6-membered rings using this sort of reaction. So, okay. We get a minus charge here. So, well, let me just write that we do another keto alpha taumerization. Okay. So we have a minus charge there, which maybe I'll draw in blue. Okay, and then these two carbonyls look pretty much the same, right? Because this whole thing at the end is symmetric. So that is just to say we could choose to attack whichever one. It won't make a difference. Okay, so here we go. We'll attack over here. And, well, let's just speed things up by a step. So this oxygen is also going to pull a hydrogen from some water. Okay. We know that in the end, it's going to be an alcohol there. Okay, and, well, while we're at it, let's just do some counting. Okay, so over here we had 1, 2, 3, 4, 5, and 6. All right, and to keep things from getting too complicated, we can use that to help us out. I guess these are pretty much like all equilibrium arrows, but, well, we're not too worried about that. So here we had 1, 2, 3, 4, 5, and 6. And that was it. Okay, so once again, we had 1, 2, 3, 4 carbonyl on 5, and 6 over here. All right, and then we heat this some more, and what happens? We dehydrate over here. Sorry, I deprived you of that question, but it's Robinson annulation, and we pretty much always wind up dehydrating it. So, cool. We're left with the ketone there. That's kind of neat. And then we get this second ring with a double bond there. Okay? This is your typical standard Robinson annulation looking structure, right? We have a 6-membered ring with this carbonyl and a double bond next to it. That's like, if you see this, it's just, it's really indicative of Robinson annulation. All right, let me grab one last problem. Do this problem. Move it down. And, well, I'm not leaving myself a ton of room for this problem, but I bet you that we probably don't need it. So here we go. We have this structure over here, and we're putting it in base. So what's going to happen to the structure?
Deprotonate the nitrogen?
Yeah, exactly. Okay. Get rid of that H. There we go. It's a minus charge instead. Okay. So now we have an N with a minus charge. And, well, that's a pretty good nucleophile, so what reaction are we going to do with this second compound?
SN2.
Yeah, it's SN2 once again. Good nucleophile. Over here is going to be SN2. Now we add this hydrazine, this NH2NH2, and we heat it. So, okay, now this is kind of weird, and alright, now this is not like Orgo-1 reactions anymore. But hopefully, by now you've picked up on the fact that we're doing a particular type of reaction. So what reaction are we doing?
Gabriel.
Yeah, so this is the Gabriel synthesis. And what does the Gabriel synthesis make in the end? Okay, maybe that was a bad question. The Gabriel synthesis makes primary amines. Okay, and this whole structure, this is just like the reactant. So it's kind of weird because like we gave you the kind of reactant for the Gabriel synthesis here, and the actual structure that we're reacting it on in here, but all it means is we're going to take this bromine and swap it out with an NH2. Okay. The Gabriel synthesis also only makes primary amines. So, well, here we go. We made a primary amine. So that's the whole thing. Okay. All this one takes is just seeing this is the Gabriel synthesis. The Gabriel synthesis makes primary amines. I'm not going to worry too much about the rest of what happens. Okay. You get an extra structure byproduct that comes from this thing at the end, but okay, well, it's the same for every Gabriel synthesis, and I don't think in this case that we're very worried about it.
Wait, in step 2, I thought this was an SN2 with the N minus, but do you wait until... Oh, that's already connected to the molecule, okay.
Yep. And then that hydrazine disconnects it from the molecule and leaves that NH2 behind. So that's all. Any Gabriel synthesis will always involve doing an SN2 like that anyway. So this
So
is no
that's
different.
the product, just this on the right side, separate from
Yep.
the molecule?
Yeah, that's it. So then there's also like something else which I think looks like this. Honestly, yeah, I can't remember for certain if it's this. This is like a byproduct of every Gabriel synthesis that you do. So, yeah, it looks something along these lines. It might be slightly different. There might be like a double bond between the nitrogen. I don't think there is, but there might be something like that. Maybe these carbonyls are different. I think they're the same. I'm pretty sure it's this. I can go check, but like, the main thing that we're worried about is this thing over here. This is like kind of the relevant part. Right. That's all of our problems. What would I hit? Stop record.